Dann machen wir jetzt weiter mit KI, mit genau Machine Learning Models und wie diese für Predictive Maintenance genutzt werden können. Ja? Predictive Maintenance, die vorausschauende Wartung, so einer der großen, immer wieder genannten Use Cases rund um das ganze Thema Digitalisierung, Smart Manufacturing etc. Und darüber erfahren wir jetzt von Patrick Rockenschaub.
Genau.
Vom Fraunhofer IKS, also es geht um Machine Learning Models für Predictive Maintenance.
Genau, danke.
Bitte schön.
Right, good afternoon. Thank you all for joining me here today. My name, as you've heard, is Patrick Rockenschaub, and I'm a senior researcher at the Fraunhofer Institute for Cognitive Systems, which is here in Munich. I'm quite delighted to talk to you here at Automatica about predictive maintenance. And this predictive maintenance is something that becomes more and more of interest to industry. Machine learning is a big topic we see throughout the Automatica here, AI is everywhere. So I'd like to share some of the experiences and insights that we've made working in that field. So today's talk, where do I actually, is that for pointer? So today's talk is trying to give a high-level overview and focuses specifically on how do we evaluate these models. So we are going to already assume that we have our model fit. That's something many people now know to do, but the next question is, how do we evaluate this? How do we do this properly? How do we ensure that this is fit for purpose? Right. As I said, it's going to be a rather high-level view, but I hope that there's something in there for everyone. I just want to make sure that everyone understands it. Do I click? No? Is this the right? Green button? Oh, this one. There we go. Didn't look like a button. Perfect. So, right. So I want to start off with what is predictive maintenance, just to make sure that we're all on the same page. It's going to be a refresher for those of you who know it already. For the rest, predictive maintenance is really just the proactive maintenance strategy. We try to use all sorts of data that we collect about the machine to predict when these machines actually need maintenance. So we want to know when is a failure likely to occur, and we want to react to that and schedule optimal maintenance. So we have a system of some sorts. It could be a factory, it could be just an individual machine, it could be many machines, and these are operating in daily business. And there's more and more sensors now deployed in these machines that are continually gathering data about the operating of that machine. And so we measure all of that. It could be temperature or rotation or whatnot. And what we really want to do is to feed this to a model of any sort, a predictive model. Originally, they tended to be physics-based, based on what we know about the world, but use cases became more and more complex, so there is more data-driven machine learning, AI, used to do that prediction task now. And the idea of all of this is, of these models, to make a prediction about something that we care about. Typical examples here would be, you want to know when there's a fault in the machine that might not be obvious, but may propagate itself and leading to the destruction of the machine. And simultaneously, you might also want to know how quickly is that going to happen, like how many days, how many hours, how many minutes do we have left until that point. And then we want to make some decision based on this, usually doing some sort of maintenance. And as I briefly teased in the beginning, what we are focusing in here is how do we properly evaluate this system once we have it. For this, I'm going to use a running example for out of this. So it's some small data set provided by NASA, and it's about jet engines. You see a graphic of that jet engine here. It's a turbofan. That's about all I know about this thing. I'm not a flight engineer. I'm a data scientist. But these have sensors throughout that jet engine that measure certain things that are important for those positions. And the data that comes out of this looks like something on the right. So these are 10 example jet engines. And we see that over time, so the x-axis here is how many flights do we have left. Over time, these sensors seem to change a little bit, the things that they measure. So there's some change in the underlying engine. But by just looking at that picture, I at least would not be possible to tell you how many more flights does the engine have left. And that's really kind of the promise of machine learning. We're trying to have a machine pick that up. to give you a bit more detail about this data set, because it's important for what comes afterwards, is it's a relatively small data set. We've got 100 engines for training and about 100 engines for test. All of them are run to failure. So we run them for as long until they break down. And there's 21 different sensors throughout those engines that collect data throughout the flight. And the task for the model that we have is actually, tell me after each flight, how many flights do I still have left? And to give you a bit of an idea what the target function looks like, that's maybe more for data sciencey people. It's on the bottom. So on the left, we've got a turbine with a short lifetime. That's just an example of 3 flights. So it broke down after 3 flights. And we have this true line of the blue one that you can see that shows you after each flight there's one less flight left, right? It's a pretty easy target function. On the right, you've got another engine that has 9 flights that it totally operated until it broke down. And so really what we want to do is, after the first flight of the first turbine, we want to predict like how many flights do we have left. Here we said roughly 3 probably. We were off a bit too optimistic. We said 3, it was only 2, so we made a little bit of error. Next time we underpredicted a little bit, and then this thing broke down. And the same we can do for the next engine and for all the other engines that we have. So this is what our model is tasked to do and how it operates. The question is then, how can we measure how well this thing is doing? Is it doing a good job? Is it doing a bad job? How do we know? So the most common thing that's used throughout the literature, you see that everywhere, is what's called the root mean squared error. Those of you who have ever done machine learning will know that one. Those who are like equations, they see the equations up there. But for everyone else, it's essentially want to know on average, how far off are we from the truth? Right. So you see on the left-hand side, again, an example engine. Blue is the ground truth, what was actually the case. And the orange bit is what the predictions that we made after each flight. And so we measure how far we're off in the first prediction, and we do the same thing for all the other predictions. And more or less simplified, we average across that, and then we know an average across all the engines, and then we know how good we were on average. And if you look into the literature about predictive maintenance, you see that metric everywhere. And so here's an excerpt for more or less the best model on that particular data set by year. So the data set has existed for a while. And so you can see that, and generally, on the third column on the left table, you see the RMSE that these models were able to achieve. And in general, these kind of decreased over time, with the exception of a very good model that someone proposed in the beginning. And they kind of stabilized in later years at between 10 and 12 RMSE. And so these are where the kind of benchmark top models are. And we took a look at the same data set and we're interested, okay, first of all, can we reproduce this? Is this reproducible? So we applied the same thing, and you can see the results on the right. So we fit 2 of the models you see on the left and a new model, and just looked how well did we do. And the first observation, I guess, is we also achieved that area of 10 to 12. So we seem to be able to match the state of the art. And we also, what the literature usually, unfortunately, doesn't give you, we also give you some uncertainty around that. So you can see that for the TimesNet, it's actually right, the uncertainty is right between this 9.9 to 12.3. So we were able to reproduce that, that's good. Second observation that you might make is, well, the CNN, our CNN performs much better than the CNN in the literature, which seems to indicate at least that if you had done proper training in 2016 on the left, you might have already kind of achieved the state of the art that we're here. So there wasn't, model-wise, there wasn't too much improvement over the last year. There wasn't some miracle model that did everything better. But ultimately, the big question when we look at this now remains is, well, are these models any good? Are they actually fit for purpose? Like, what does this RMSE mean at the end of the day? And once you get to that question, you need to take a step back and perhaps think about the 2 main things that we're interested in for predictive maintenance. On the one side, one of our main goals is safety. You want to make sure that this engine doesn't break down during a flight. So we want to, before the last flight, say, well, look, just don't. And that is a policymaker is a typical user for this, maybe inside the company or federal. We just want to make sure that there's never an engine starting that's faulty, and there's an emphasis on predictions that are very close to the failure time. On the other hand, we could have a goal of maintenance, like there's a fleet manager, and the goal here is really the standard goal of predictive maintenance. We want to not maintain too often, but also definitely don't maintain too seldom. We want to find just the right spot of maintenance. And here it's really, there's a different emphasis here, which is, can the model predict sufficiently early at the given time? Let's say we need 40 flight cycles, which is, I don't know, 1 flight per day, so 40 days to replace that engine, to order a new engine, put it in, have it fly again. Then we want to have really good prediction at that particular point, 40 cycles before this thing breaks down. And the main problem is RMSE cannot give you that. It's pervasive through all the literature, but it doesn't give you. And as an example here, you have 2 graphs that are done by some hypothetical model on a hypothetical jet engine. And you can see the A and B, left and right, perform quite differently. So whereas A performs quite well in the beginning, is right on spot, it gets worse over time. And towards the end, just before failure, it still thinks we've got many, many flights left. On the other hand, the model B is quite the opposite. It does bad or not as well in the beginning and then becomes better and better over time. And you can see for the policymaker, like the time right at the end is the important one. And for that one, obviously model A is absolutely not usable, whereas B is quite usable. The problem is, RMSE, these 2 models have the exact same RMSE as they're displayed here, so there's no difference between them. You wouldn't be able to tell. And to complicate matters a bit further, the fleet manager, who cares about the 3rd prediction in this graph, for them, RMSE actually work because they perform equally well here. So there's quite a nuance depending on what is it actually that you want to get from these models. And model B could be fit for model A could be fit for purpose for the fleet manager, but not fit for purpose for the policymaker. Right, so that is essentially the entire problem setup. What I'm trying to do now is give you 2 brief, relatively simple examples of metrics that could solve that, and can show you that if you think hard enough and really create the metrics in a way that they reflect what you're interested in, that you can solve that problem. The first option you have is something called the prognostic horizon. So what we're trying to do here is we want to make sure, or to kind of get an estimate of how long before the machine, the turbine, breaks down, are we actually doing good predictions? And the way we do it is we just create a cone, a boundary around our truth. You see that in the dashed lines of alpha, which we consider the acceptable error, kind of like. We don't expect to be spot on, but we want to be close. And then we just count, essentially, for each jet engine, how long before the end were we continuously within that channel, which gives us a time of how many flights have we actually done a pretty good prediction. So that's one option, and that's obviously something that a policymaker might care more about than the root mean squared error. A second thing that we could look at is something called alpha lambda accuracy, and it's not that different. It's also quite simple as a concept. We do the same boundaries of acceptable error, same channel, and essentially we just pick from domain knowledge, from what we know about how our maintenance process works, pick a time that's very important to us. Let's say the 40 flights ahead, because that's the time that we need to order a new jet engine. Then all we really care about is for how many of our jet engines have we done a good prediction at that particular point in time. That's something the fleet manager may care about. So these are 2 relatively simple, it's about as simple as it gets, metrics that you could use to get more information into your problem. And I also now want to share with you based on these metrics, what would happen to our models that I've shown you before, where we had no idea whether the RMSE was any good or not. Let's say we've got 2 requirements. For a policymaker, our model should have a reliable estimate at least 2 flights before the thing breaks down. So we've got time to react, cancel the flight, just stop it. For the fleet manager, on the other hand, we want to know that 95% of our engines have a good prediction 40 time steps, 40 flights ahead. And so what we found when we did this, we actually found that for the policymaker, the middle column is important, the pH, and the LSTM, a type of neural network, was the only one that fulfilled that criteria. Barely, I admit, but it did fulfill it, so it would have been the most suitable one. For the alpha lambda accuracy, on the other hand, none of our models achieved the high standard that we set it. So 70% was the highest, again by the LSTM. So, and just remember, on the left you see all of these were state-of-the-art models, and in literature there's been hundreds of papers on this data set achieved what they achieved. So from this we would conclude, actually, we want to choose the LSTM, despite having a slightly lower RMSE, which is within the variance, but still. And it would be probably suitable for policymaker. We could do more metrics on it, but it would probably not be suitable for this fleet manager of ours. I've hinted also that these are just some metrics that you can look at. There's many, many more. I've just name-dropped a bunch of them. There's also custom ones that you can design to your specific problem at hand. And what's maybe also, as a brief aside, important, if you think about them soon enough, like from the start of your project, it should be clear what the user's looking for. You can integrate them into your training process. And you can actually try to fit the models in a way that they are more suitable to that particular goal you care about. That brings me mostly to the end of my presentation. I think the main takeaway should be, in this area where AI is now everywhere, and it seems like everyone can do and will do AI, but the safe and meaningful evaluation of those is important. And for predictive maintenance, not only, I guess for every other use case that you think of, you must combine this technical know-how, this knowing of how to fit a neural network, which is important, but it gets easier and easier, with this kind of user-centric, end-user-centric view. Take into account what the user cares about, what they need, and then evaluate your model with regards to that, so you can be sure that it's actually useful in practice. Yeah, so I think we've got time for some more questions. If you can't get your questions in now, you can also come talk to me later at the booth just over there, 129 it is, and we can talk there. And I'll also hover around here after the thing.
Okay, cool. Thank you.